In my last video, which I've since removed, I attempted to go into detail about CPU cache and writing more performant code. I was wrong on some pretty crucial details, so I'm back to correct that. I don't want to contribute to the sea of code misinformation regarding performance. I'll be going over those points and then I'll move on to talking about Godot's server APIs. Firstly, the ordering of variables. A minute detail, but assigning or creating variables near the point you use them is preferred. This reduces the number of misses the CPU will go through to find that variable. While assigning variables like this is true, the difference is so small it's essentially non-existent. Don't bother doing this, especially within GDScript. Local pointers to global variables, No, this makes almost no difference. Creating a pointer is just assigning a new reference that will be garbage collected at the end, in GDScript's case. This differs slightly for the type of variable, but there is no real benefit to doing this. If you know the data you are working with, why make the compiler assume? This is just wrong. GDScript is tokenized, parsed, and then compiled into bytecode at runtime. Compilers are not guessing. To conclude, CPU cache is not a point of interest in any GDScript code. These incredibly minuscule gains can be completely mitigated by a single append call. Do not worry about caching with GDScript, it's a high-level language. Anyway, with the misinformation cleared up, I'm going to move on to the section for Godot's server APIs, and this is carried over from the deleted video, but with a bit more information. Now let's talk about Godot's low-level APIs. With more and more items being added to my world generation, things like collisions, navigation maps, animals, forageables, etc., I needed as many frames as I could get. The biggest slowdown regarding Godot is introducing changes to the scene tree, things like adding nodes and instantiating scenes. I could write the fastest code ever, but it would not affect scene tree changes. That is fully behind the scenes. But what if you just don't access the scene tree? By avoiding the biggest bottleneck entirely, I can run my world generation at speeds dependent on my code, which can actually be improved upon, unlike add child. To start, in one of my first videos about the world generation, I talked about using multi-meshes or mesh instances to add decorations. To solve this draw call issue, I switched to using individual mesh nodes for each decoration. Now, that was the first bottleneck for me, having to add so many children to the tree. What I ended up doing was utilizing Godot's RenderingServer for them instead. So instead of adding mesh instance nodes to the scene, I used the RenderingServer's instance functions to spawn meshes with the lowest API possible. I no longer have to deal with objects like Node 3D, Mesh Instance, Sprite 3D, etc. since the RenderingServer only uses RIDs. These RIDs are not reference counted and are not collected or freed by garbage collection. That is entirely up to me to handle. As you move lower into Godot's API, they leave it up to you to handle things you don't normally have to worry about. This means less overhead though, and the less there is, the better. Since I use RIDs and whatnot, I have to be more careful about my data structure and what I'm instancing. Even without the most optimized code, I was able to get substantially faster speeds since I'm dodging the scene tree. To be in line with low-level APIs, I decided I was going to do the same with the Navigation Server 3D and Physics Server 3D. Those two required slightly more detail and care, but having almost no nodes for visuals, collisions, and AI navigation is very lightweight. Another great thing about these APIs is the fact they are very CPU cache friendly. They're designed for dense structures, all of them using RIDs. There is very little object-oriented data moving around, which is inherently cache unsafe. A lot of these lower APIs are thread safe as well, since their processes are already attached to their own thread. Scene tree access is always thread unsafe since it relies on the main cycle to access. Moving to lower APIs ensures the functions you are calling are safe at any point. For reference, this is all I do to create a decoration and have it be visible to the player. For my case, I get the rendering server's instance mesh based on its distance to the player when generated. Afterward, I create the instance, set its data, and store the RID data. Since the rendering server does not support LODs like a mesh instance 3D can, I do it manually. Instead of checking every object and its distance, I only check the chunk it's in a squared distance check. Since I don't have nodes, I have to hot swap the mesh as the player moves. Normally this would be expensive, but preloading the meshes and using the rendering server nullifies most of this. Similar to the CPU, the GPU loves when things are the same. Since each unique decoration uses the same texture or mesh, every oak tree has the same texture, Godot can pass every oak tree as a single complete draw call, making the cost of them almost non-existent. The only expensive operation is the mesh detail itself. Now let me move on to how I use the physics server. Typically, procedural world collisions tend to be a more convoluted and dense system. You're no longer working with simple shapes or pre-made meshes. Luckily, Godot has a collision shape called Height Map Shape 3D. Since my game does not allow for caves, I'm able to use this shape. If you were to create a voxel type terrain with overhangs or caves, you'd have to implement a separate collision system to support non-flat coordinates. This is how I create and add the collision shape to the pool. I'll explain why I use a pool of colliders in a bit. Firstly, I create the collision body and its shape on the server. I then set this body in the world and configure its modes. Afterward, I configure the height map shape since it needs default data. Once the shape's data is complete, I can safely add the collision shape to the body. I immediately disable the body as well. Now you may have noticed the debug mesh line. Usually in Godot you can simply toggle visible collision shapes in the running program to view colliders. This, however, is reliant on the nodes being present in the scene. Since this type of collision data does not contain nodes, you will never be able to see it. I created the debug mesh so I could toggle it on or off to see the generated colliders. Once this collision shape is all set, it's ready to be manipulated and assigned to a chunk. Here's where I employ the heavy pooling. Since chunks use LODs, the collision data needs to match that as well, since in some cases, the finest detail for a chunk has not yet been created. Thankfully, collision shapes can be easily scaled by mapping the lower resolution vertices and simply dividing the height by the scale, then scaling the transform. For example, if an LOD has 4 times less detail, I will divide the vertex heights by 4 when adding them to the height map. Then I will scale the transform by 4 once completed. You can scale collision shapes in Godot, they just have to be perfectly uniform. You cannot scale it up by only the X and Z, hence why I divide the heights then multiply all of it back. This ensures the collision shape is nearly identical to the level of detail. Onto the navigation server. It is nearly identical to the mesh creation, except I have to convert the indexed vertex data to its non-indexed variant to cooperate with the nav server's expectations. It's just a matter of stealing the mesh data and filling with it. After that, I add the faces to the navigation source data, then bake it asynchronously. But that's about it for the service level introduction into Godot's servers. I appreciate everyone's feedback and criticisms in the last video though. Hopefully I won't make as many mistakes in the next video, which will be about compute shaders.